Okay, thanks guys. Thank you for having me. So yeah, today I'm going to be talking about the chromatic Null-Stellensatz, and everything I say will be joint work with Robert Birkeland and Tomer Schlank. So the story begins with Hilbert's Null-Stellensatz, which is a theorem that gets a lot of commutative algebra and algebraic geometry off the ground classically. And what it asserts is that if I have K an algebraically closed field, and I have f1 through fn some polynomials over K, say in m variables, such that the ideal generated by them is not the unit ideal, then you learn that these polynomials will automatically have a common root. So it's something kind of amazing where you can check a condition on just like sort of combinatorial about whether an ideal contains one, and then learn whether or not some polynomials have a common root. But there's an equivalent way that you could state this that's a little bit less hands-on, which is that you could consider the algebra generated over K by adjoining, well, the corresponding algebra K adjoin x1 through xm, and mod it out by these polynomials. And the assertion of the Null-Stellensatz is saying that well, I guess this algebraic variety has a point, or in other words, there's a map back to K. So that's like a common root because it's sending x1 through xm to some numbers in K satisfying these polynomials. And of course, this map back is a retract of the unit map. And so the assertion of the Null-Stellensatz is that in this situation, the unit map, so when K is algebraically closed, the unit map of any finitely generated algebra admits a retract. And the nice thing about saying it this way is that it's a condition that doesn't really refer to elements, and all these concepts you can have analogs more generally in a categorical setting. So you can make a definition. So for C, any symmetric monoidal category or infinity category, you can say what it means for an algebra to satisfy Null-Stellensatz. So a commutative algebra, which we'll suggestively call K, in the category C, satisfies Null-Stellensatz if for any compact and non-terminal. So compact is like finitely generated, and non-terminal is non-zero. Oh, so I guess I should have said non-zero. So for any compact non-terminal commutative algebra A over K, the unit map of that algebra admits a retract. So I've sort of just restated. So the first example of this is that, well, if C is the category of abelian groups, then the algebras that satisfy Null-Stellensatz are exactly the algebraically closed fields. But the focus of today is I want to say what happens in a chromatically localized setting in the Tn and Kn local categories. And so to do that, I have to introduce the object in question, which will turn out to be the Lube and Tate theories. So I'm just going to review these briefly to set some notation. So these Lube and Tate theories were first introduced by Morava And subsequently, they were studied by Gorse, Hopkins, and Miller and Lurie, who produced these as commutative or E-infinity ring spectra. And the construction involves two inputs. So it involves a perfect field K of characteristic P, and a group G0, or sorry, a formal group G0 of height n. So n is some integer which is at least 1 over K. And from these two inputs, they produce a commutative ring spectrum En of K and G0, which is a Kn local E-infinity ring spectrum. So a priori, this construction certainly depends on the group G0, but for the rest of this talk, we're essentially going to be interested in the case when the field K is algebraically closed. And in this case, all formal groups of a given height are isomorphic, and so we won't display the dependence on the formal group, and we'll just say En is En of K. So in this situation, you can the homotopy groups of this object En of K are the Witt vectors of K adjoined n-1 power series generators, each in degree 0, and a single periodic generator in degree 2 called U. And the relationship to sort of the notion of being algebraically closed was, I think, first noticed by work of Baker-Richter. So our work is sort of inspired by that. And what they showed was that if I take the Lube and Tate theory over FP bar, then that has a similar sounding property. So it emits no non-trivial connected Galois extensions. And this notion of Galois is in the sense of Rognus. We define what it means for a map of ring spectra or a ring spectrum to have a Galois extension. So given the definition that we made above, one can give the following extension of that theorem. So this theorem is joint with Robert Birkeland and Tomer Schlank. So it turns out that a commutative algebra A in Tn local spectra, or if you like Kn local spectra, satisfies null-Stellensatz in the Tn local category in the sense defined above. Sorry, I'm gonna switch this orientation so maybe more is visible. Please let me know if things get too small. So an algebra satisfies null-Stellensatz if and only if that algebra is equivalent to E of L for some algebraically closed field L. So this is a generalization of the classical theorem, but what I want to focus on is actually what turns out to be a critical ingredient or core element of proving this theorem, which is simpler and has some implications. And in order to explain what that ingredient is, I want to give a cartoon of the proof of the classical null-Stellensatz. So here's a proof cartoon for Hilbert's theorem. So just to remind you, Hilbert's theorem is about an algebraically closed field K and a finitely presented algebra over K. And the situation is that you're trying to find a map back to K. And the first thing you do when you prove this theorem is you don't try to map back to K, but you try to map back to any field at all. So you choose inside a maximal ideal. Whoops. And once you have a maximal ideal, that gives you a map to a mod that maximal ideal, which is some field K prime. And because A is finitely generated, this K prime is also finitely generated as a K algebra. And that then what you do after that is you analyze finitely generated field extensions. And it turns out that, well, this turns out to be most of the work. One is sort of totally trivial. But it turns out that field extensions, which are finitely generated as algebras, are always finite. So you prove this fact in commutative algebra. And that tells you, because K is algebraically closed, that K prime equals K. So you can try to run this strategy in the chromatic setting as well. So in the chromatic setting, let's say the chromatic setting, then the analog of that algebraically closed field K we're claiming is something like En of K. And we still have some algebra which is compact, so that's like, it has some finiteness condition. And it turns out here that actually step one is the problem and not step two. So step two, once you have step one, you can accomplish step two by sort of a similar argument. But to do step one, you'd need to map that to some analog of a field. And so you in this chromatic setting, it would correspond to making a map of rings, of E infinity rings, to some En of K prime. And that's sort of not immediate. So one is non-trivial chromatically. And the reason is that quotients are poorly behaved. You can't say that like your algebra A has a maximal ideal and you can just quotient by it. Because in general, if you have an element in a commutative ring spectrum in pi zero, you can't quotient and still remain a commutative ring because of the existence of power operations. And to be very explicit about this, we can say what the problem is at height one, say exactly what the problem is. So if I have a K1 local E infinity ring A, then the point is that pi zero of A has more structure than just the ring. It's a p-typical lambda ring, or what's sometimes also called a theta ring. And what that means is that there's an operation theta, in fact, a non-additive operation theta on the pi zero. And so that means that if you want to quotient by an element and stay in this world of K1 local E infinity rings, if you kill an element X, then you have to kill theta of X and theta X, etc. So it becomes very cumbersome to quotient. You can't just hit the element you want. You have to quotient by a lot of other things too. But it turns out this is also always possible, and that's sort of the key result. So the result asserts that if I have some Tn local E infinity ring spectrum, which is non-zero, then it always admits a map out to a Lube and Tate theory. So then there exists an E infinity map from A to some Lube and Tate theory of height n. And we can just say L for some algebraically closed field L. Sort of, you can always map further to an algebraically closed one. Right. So I can illustrate what's going on in a toy model. So there's a toy model for this just in the algebra setting. So if I'm at height 1 and I'm just looking at pi 0, then pi 0 of a K1 local E infinity ring is a P complete theta ring R. And you might ask, well, does R map to the width vectors of L for some L algebraically closed? That would be sort of the algebra analog at height 1 of the thing I'm inserting, because pi 0 of E1 of L is the width vectors of L, p-typical width vectors. And the reason this happens is, well, R, you can choose from R a map to an algebraically closed field L of characteristic P, just of rings. So I'm ignoring the theta ring structure. But over L, you have the width vectors of L, and that has a special property that it's the co-free p-typical lambda ring on L. So this is like a property of the width vectors. So giving a theta ring map to the width vectors of L is the same as giving a ring map to L, and therefore you make that factorization. And so this is sort of a toy model of what's going on in that theorem. And indeed, the proof of the theorem uses a higher height analog of this co-freeness statement for the width vectors. And this higher height analog involves the power operation algebras of Resk, and this co-freeness statement was known independently by Resk as well. Okay, so for the rest of the talk, I just want to focus on this last theorem that I stated and some applications of it. So it turns out to have some applications just in homotopy theory. But before I go on, any questions on what the theorem says? Okay. So the first sort of application that I want to discuss is the topic of what I'll call chromatic support for E infinity rings. So the basic definition is, suppose I have R a P local ring spectrum. So it doesn't really need to be an E infinity ring for this to make sense. I can define the support of R, or the chromatic support of R, just to be the integers, the non-negative integers, such that the Tn localization of R is not 0. So it's the localizations that R does not vanish at. There are lots of equivalent ways you could say this. So this is of course the same as saying Tn tensor R is not 0. But by the nilpotence theorem, it's actually equivalent to require that the Kn homology, or the Kn localization of R is not 0, because R is a ring spectrum. So this notion a priori, I mean, it's not constrained at all. So even for associative rings, there's no constraints on what the chromatic support of a ring could be. But it turns out that for E infinity rings, for commutative ring spectra, it's highly constrained. And the first hint at this that I know is a theorem sometimes known as May nilpotence, which is due to Matthew, Neumann, and Noel. And essentially in this language, what the theorem asserts is that for R, say R from now on a commutative ring spectrum, for a commutative ring spectrum, the support of R is either empty or it contains 0. In other words, if a ring spectrum is to have a non-zero Tn localization for any n, then it must also be rationally non-trivial. And this theorem was greatly generalized by Jeremy Hahn. And Hahn's theorem says that the support of R is in fact even more constrained. It has to be a closed interval, 0 to n, for some integer n, which is between -1 and infinity. So when n is -1, I'm interpreting this to be the empty case. In other words, if a ring spectrum is Kn acyclic, or Kn plus 1 acyclic, then it's also Kn plus 2 acyclic. Right. And one really great thing about this theorem is that it allows you to make a definition. So it asserts that every E infinity ring spectrum has a well-defined integer n, which is the height. So we'll define this n here to be the height of R. And I want to emphasize again, this is the thing about commutative rings. This sort of doesn't make a lot of sense for a general ring spectrum. And so we can give a little table that gives the height of our favorite commutative ring spectra in this sense. So at height 0, you have things like Q or ZP or Z. It's the ordinary homology with non-torsion coefficients. And so under this definition, at height -1, you have FP, because FP tensor Q, the height 0 component of that is 0. So its chromatic support would be empty, but whatever. So at height 1, you have things like real and complex K theory. So their Kn localizations for n greater than 1 vanish. We also have the connective variance. And at height 2, you have things like TMF or height 2 Lube and Tate theories. Of course, at height n, you have the height n Lube and Tate theories. Things like that, like things like elliptic cohomology. So this sort of jives with the usual notion of height, at least for 0, 1, and 2. So using the result, the main result about any non-trivial Tn local E infinity ring mapping to E theory, we can give an alternate proof, sort of overkill proof of Hahn's theorem. So suppose you have some E infinity ring spectrum whose Tn localization is not 0. So that means it's supported at n. Then we want to show that it's also supported below n. So we want to show that the Tn -1 localization of R is also non-zero. So to do this, well, that ring R maps to its Tn localization, of course. And because this Tn localization is hypothesized to be non-zero, the main theorem that I stated implies that you have a map to some Lube and Tate theory of height n. But you can just take this ring map and make it and localize it at height n-1. So I can take the Tn-1 localization, and I learned that there's a ring map from the Tn-1 localization of R to the Tn-1 localization of En of L. But you can just calculate that when you take a Lube and Tate theory, its Tn-1 localization is not 0. And this is a map of rings. So if the target is non-zero, then the source is also non-zero because the 0 ring has no non-trivial modules. So that gives a proof of that. I mean, hiding in this proof is the same sort of power operation argument that is needed for Hahn's theorem. So this isn't really, you shouldn't see it as like a magical improvement or anything. But what it does give is a sort of a witness to the height n-1 part being non-trivial. It gives like a ring map that witnesses that, and that turns out to be to have further applications for chromatic support in the form of applications to Redshift in algebraic K-theory. So I don't have time to give a full overview of this, but I just want to say briefly what the picture is. So algebraic K-theory is a device through the work of many people that we can apply to a commutative algebra in spectra and get another commutative algebra out. And so Assoni and Rognus studied the algebraic K-theory of the form of connective topological K-theory. And they realized that this K-theory, when you plugged in a height 1 object like connective topological K-theory, was sort of height 2. And they had many more specific things that they were able to say about it, like real computational things. And they proposed what's now called the chromatic redshift conjecture. So this turns out it's like a big web of conjectures, and they're very precise conjectures about how K-theory should behave. And today, unfortunately, because of time constraints, I'll just state a weak form of this conjecture that we're interested in. So here's a weak form of the redshift conjecture. Which is something just about the behavior of this chromatic support for commutative ring spectra. So one form of this philosophy is that if R is a commutative ring spectrum, then the height of the K-theory of R should be the height of R plus 1. So if you could wonder if just this numerical thing is true. And this conjecture has had a lot of breakthroughs recently. And I'll have to leave out a lot of them, but I just wanted to state a couple. The combined work of many authors, Lan, Matthew, Meyer-Tama, and Clausen, Matthew, Neumann, Noel, in oversimplified terms, says that the height of K, they showed that the height of the K-theory of R is at most the height of R plus 1. So algebraic K-theory may redshift, and if it does by at most 1. And this, relative to the form of the conjecture I stated, the remaining question is, well, does that redshift actually happen? Is this actually an equality? And this was addressed in the breakthrough work of Hahn and Wilson, where they showed, well, not for an E infinity ring, but for a BPN, that the Tn plus 1 local K-theory of this ring spectrum is not 0. So in fact, they show much more. So they show something about analogs of Quillen-Lichtenbaum for BPN. And just purely in the height shifting situation, there's also a preprint of mine that computes the height of the K-theory of these Lube and Tate theories. So for any of these, you can also show that the height is n plus 1, so that this redshifting happens. But a corollary of these results and the result that I stated is that, in fact, for any E infinity ring, you can demonstrate this height shifting behavior. And the proof is along the lines of this proof of Hahn's theorem that I showed. So if I say that the height of R is some integer n, then again, R maps to its Tn localization, which is non-zero, and therefore that, by the theorem, maps to some Lube and Tate theory. And now, instead of just localizing this ring map, I can take K theory of that ring map. So I can apply algebraic K theory and obtain a ring map from K of R to the K theory of this Lube and Tate theory. And now what we're interested in is the height n+1 part. So we'd like to say something about the Tn+1 localization of the K theory of R. So we can Tn+1 localize this map. And by the above quoted result, this redshifting happens for the Lube and Tate theory. So this Tn+1 local K theory of the Lube and Tate theory is not zero. And again, this is a ring map. And so that implies that if you have a ring map from this Tn+1 local K theory to a non-zero ring, then that itself is also non-zero. And that proves it. So somehow you're seeing that having this map to this Lube and Tate theory is controlling what K theory does once you know what it does for Lube and Tate theory. So on the topic of sort of mapping into Lube and Tate theory, we get some other applications to the theory of orientations of E. So the motivation behind this is sort of you can note there's an immediate thing you can say, immediate corollary of the theorem, which is that because the Kn localization of mu is not zero, the theorem implies that mu, while it maps to its Kn localization, which is a non-zero Kn local E infinity ring, and therefore it maps to some Lube and Tate theory for some algebraically closed field L. And this is a commutative ring map. But so having this map is an immediate corollary of the theorem, but it turns out that you can do a little bit better. So it turns out it's not just some Lube and Tate theory, but in fact you can make a map to any Lube and Tate theory. And this is something special about mu being a Thom spectrum. So the general phenomenon that's going on is something that we call universal orientability. This is a corollary of our theorem. And the situation is that suppose you have a map of connective spectra from X, a connective spectrum, to pick of En of K. So you're supposed to think of this as you have loops infinity of X, a space. Oh, sorry, I should have written that it's a map of connective spectra. So loops infinity of X is a space, and you have a map from loops infinity of X to the groupoid of invertible En of K modules. So that's like a bundle of En of K, or invertible En of K modules on loops infinity of X. It's the sort of thing that you can take the Thom spectrum of. So, and if you do take that Thom spectrum, that's going to be some commutative algebra over En of K. Sorry, I should have said. So for the rest of this talk, we're fixing K in algebraically closed field. Any algebraically closed field. Okay. So again, so this data and the data required in the theorem is a map of connective spectra, which gives you a Thom spectrum MX, which is a commutative algebra over E, namely the colimit of these invertible modules. And in this situation, the theorem asserts that there exists a commutative ring map, commutative E algebra map from MX to the Lube and Tate theory, if and only if the Kn localization of MX is not zero. In other words, the only obstruction to having an orientation is if your Kn locally zero as a ring. So the example of this that I was mentioning above is that, well, if I take F to be the J homomorphism, so X being BU, take the J homomorphism to pick of the sphere, and I compose under the unit map to pick of En of K, then the Thom spectrum is, well, it's just the Thom spectrum of the J homomorphism tensored up to this Lube and Tate theory. So it's mu tensored up to the Lube and Tate theory, and because the Kn localization of this, the Kn homology of this is not zero, you get an E algebra map to mu, or sorry, to E, and that gives you the map above. But there's a sort of another family of applications of this orientability theorem. So essentially what it's saying is that, well, having a commutative algebra map from MX to En of K, that's another way of saying this map F is null homotopic. I could have just stated it that way, because it's saying that this bundle is trivialized in E theory. And so this theorem is giving you a way to test that maps into the Picard from connective spectra are zero. And so that allows you to reproduce a calculation of Hopkins and Lurie, an unpublished calculation, which was also known to Resk at height 2. And the calculation is about maps of Eilenberg-MacLane spectra into the Picard groupoid. And what it asserts is that if A is a finite abelian group, finite abelian P group, then maps of spectra from A, considered as a connective spectrum, to the Picard of En of K is just the n plus first suspension of the Pontryagin dual of A. In other words, it's an Eilenberg-MacLane space. And in particular, maybe a more familiar form, this allows you to compute what's sometimes called the pth roots of unity in Lube and Tate theory. So that's defined as the maps of spectra from CP to the units of E theory, units of Lube and Tate theory. And because the units, the Picard is just the delooping of the units, the above theorem allows you to compute this, and you learn that it's nth suspension of CP. And to finish off, I just wanted to state a couple well-known corollaries of this. So I think the deduction of the corollaries is not super new, but I wanted to state them. So this has the following well-known corollaries. So one of them is that you can identify the fiber of the natural map from the units of E theory to its Ln localization. So one way to think of this is that you have the units which control like orientations of E, and then you have the part which is Ln local, which is like what's understandable via the Resk logarithm. And then this thing F, the fiber, is sometimes called the discrepancy spectrum. And so this fiber F was studied by Ando, Hopkins, Resk. And they showed that it was it's torsion, and well, it's sort of clear that it's torsion from the sequence, but they showed that it's n truncated. But having this calculation of the units of E theory allows you to actually identify it, or at least its connective cover. So the connective cover of this discrepancy spectrum is equivalent to a sum of two things: the connective cover of a suspension of the Brown-Combinus dualizing object, and some extra terms that are the torsion part, just in pi zero, the torsion part of the units of the base field K that you plugged in. And finally, so this sort of follows from knowing that various maps into GL1 of E are zero. And finally, another corollary, which is due to work of Barzel, Carmeli, Schlank, and Janowski. And it's a thing that they call the chromatic Fourier transform. It asserts it's a duality phenomenon for the cohomology and homology with coefficients in Lube and Tate theory, and it asserts that if M is a spectrum which has homotopy groups in a restricted range from 0 to n, so the homotopy groups are 0 outside of 0 to n, and otherwise they're a finite abelian group. Oh, sorry, finite abelian P group. Then for such spectra, you have a duality. So you can you can take Anderson or Brown-Combinus duality, and that sort of flips the homotopy groups. So our notation for that is M star, because it's an extension of Pontryagin duality. So that's going to be Homs from M into shifted Brown-Combinus dualizing object. So if you're not familiar with the Brown-Combinus dualizing object, it's just you take the homotopy groups and you flip them upside down, but still between 0 and n. Then in this situation, there's a functorial equivalence. From the homology of Loops infinity of M with E and K coefficients, and the cohomology of Loops infinity of the dual of M. And now, because this is cohomology or of an infinite loop space, so this is homology of an infinite loop space. So that has the structure of both an E infinity algebra and an E infinity coalgebra. So this is a functorial equivalence of bicommutative bialgebras. And the thing to keep in mind, so this generalizes a theorem of Hopkins and Lurie in the case that M is a Eilenberg-MacLane spectrum. And the thing to keep in mind is that in the simplest case, it's saying that the K theory of B of A for A, a finite abelian P group, the P complete K theory is the same thing as the P completed homology of the Pendragon dual of A. So that's like the character isomorphism. But it's some generalization to higher heights where you change the shift to n. Okay, I think I'm out of time. Thanks.